trying to heat a mass up. You're trying to figure out how much insulation you want to use on your furnace and how close the furnace needs to be to your mass.
Okay.
Those are two interactions that work against each other.
Right,
So
okay.
you can run less amount of experiments if you do this type of
If you
design.
do this kind of, so then you could,
You can see if there's any interactive effect
And if
between
there-
the
and if there
insulation
is-
thickness and distance.
yeah, if there is, deal with it, or if there's not, keep it at that level, because you know there's no interaction. Yeah, and to me, this is, you may be reading somebody else's work too, and you'll at least understand what they did, or like you said, you'll understand why they did it, because like the furnace example, it's gonna take you a long time to do those tests, and they're expensive. And so you might understand, well, somebody did that because it was a screening test, they had to do it to save money, to save time, and they had these, they had these techniques available to them. Oh, they blocked it, they had, when they used the word, the effect was confounded. You say, well, at least I know what they're talking about. It means it got mixed in with the blocks, and I can't see it. And to me, that's the biggest value of this. So if you're reading somebody's paper like that, and they made a decision that says, but I couldn't see this because it was confounded, well, at least you know what they mean. Yeah, is everybody gonna set up these contrasts? No, I doubt it. Well, it's kind of neat math. You can learn the modulo equation, and you may see that equation, and you'll know what it is, and it's kind of clever, the approach.
It seems like it's very beneficial for high-level R&D, where we're doing our experiments and they cost so much.
And they cost a lot.
So much.
I could see that, I got a feeling that drug companies are all over this stuff. You got a study that takes 2 years to figure out the long-term effects of some drug versus some placebo, and there's no way you're going to keep the same background variables. But you got to screen because maybe there's, there's sex, or there's some genetic, or some sort of racial issues or lifestyle issues. You see, oh my God, my number of factors just exploded, and so now I'm trying to test this drug. And I got to do 1,001 subjects, and it's costing me $1 billion, and I want to do it in a hurry because I want to get my drug to market before a decade ends. So I could see how the companies like that would be all over this. For us at Y12, probably not. Maybe at the lab you might have enough data over enough time on some of these big experiments that you might have that. But, so anyway, back to this thing. The point was, we had a big error. And remember, the error's in the denominator, and if it's in the denominator and it starts making our f small, we're not going to see things. Because remember, we're always asking whatever our effect over the error. That's our f. And if f is 1, no. If we want f to get big to see an effect. So if this is big, that just messes us up. And so the comment is, looking at this, that's kind of big. So this may be a flawed experiment. In other words, maybe we just got too much error, and so maybe we don't want to conclude that A, B, and C didn't matter, because that's what we concluded. But that error was big. Maybe we would like to, suck up, spend the money, do a whole nother replication, and get a better error term. Because if we don't have at least, if we don't have at least one replication, we don't have a real error term. We've got that surrogate error term. And now we could do it with a 2 to 3 if we compound the ABC. So we might have 3 levels, low, medium, and high, compound the ABC and let that be our error. But again, it still may be too high. I haven't done that, I don't know. It still may be too high, it still may have the same problem. So again, remember, with these conclusions, I always try to tie it back into the whole title of the subject, design of experiments. What do you want to do to change this statistical experiment, if you will, that we did to make it better? Because the whole point of the experiment was to ask ourselves, did A, B, and C have an effect? And yeah, we answered it, they did not, but ooh, be careful, because our error was big. Maybe we need to do a little bit of a better answer. Maybe not. If that error was small, we said no. Okay, it's okay to come up with no. It's okay to say A, B, and C don't matter. If we're sure of what we say. Okay, so now let's see. Let's say we had more blocks. So we've got 2 levels, low and high, some number of factors, F, A, B, and C, 3, A, B, C, D, E, 5. Now let's say we have to have 4 blocks, because gosh, it's even worse. Take forever. all day. So remember when we had 2 blocks, we had one effect was compounded. However we arranged it, we had the A or the B or the AB compounded. Well, extend that thought without proof. Well, 4 blocks means we're going to have 3 compounded effects. All right. So now we get to choose 2 of them, but the third one is kind of automatically selected by our choices. They're going to state that without proof. But kind of back of the hand, because one block is another block times any one of the other elements. So you can see how once you pick 2, then the other one is kind of constrained. So let's see. So for example, let's say we just out of the blue, I will say that we wanted to compound ABCD interaction, a high order interaction, and an ABC interaction in a 2-level, 4-factor experiment. Okay, so let's kind of look at it. Let's think about it a minute. So maybe block 1 is our primary block, our base block, the one that has the everybody low experiment in it. The block 2 is the one that compounds A, B, and C, and D. Block 3 compounds A, B, and C. Well, what would block 4 do? Look at this very interesting thing. I compounded A, B, C, D in block 2. I compounded A, B, C in block 3. Let's multiply those 2. A squared, B squared, C squared, D. Let's mod it with 2. Why are we modding the exponents with 2? Because it's a 2-level. Mod all the exponents with 2, that becomes a 0, that's a 0, that's a 0, that's still a 1. We modded 2, we get a D. So that says that the motion, from here to here, the product of these 2 is just, this block multiplied by D is just like that block. And so it says, oh, we've compounded D with block 4. And it makes sense. ABCD is sort of ABC with just a change in D. And so it's like, oh, no, we don't want to do that. That's terrible. We compounded one of our main effects. No, bad. Let's not do that. So let's figure out how we can do something a little better. And that's example 8.4. Let's see if I got it. Okay, yeah, so 8.4 says we've got a 2, 4 factorial experiment, 4 blocks. Let's compound ABD and ACD, and let's see what else is compounded, and let's divide the blocks up. All right, so let's see. Let me pull it up because I've got that statement here too. Okay, so we've got we want to compound ABD and we want to compound ACD in our first 2 blocks. Block 1 is the primary, block 2 and block 3. So what's automatically compounded in block 4? Well, let's multiply them and mod 2 and see. A squared, B to the first, C to the first, D squared. Mod 2, that becomes a 0, that's a 0, that's a 1, 1. So we've automatically compounded the BC. That makes us happy. I didn't automatically compound an A, didn't compound a B, didn't compound a C, D. Okay, so now let's map these things. Let's map this to blocks. We're going to have 4 blocks. So how do we map that? This is cool. We have 2 contrasts, right? The first contrast is the one for ABD, right? That's going to assign those guys. The second contrast is for the ACD. Okay, so since I could write my own contrast, I didn't use X1, X2, X3. I used A, B, C, D, so it's a little bit more clear. So this first contrast is the high-low A, high-low B, high-low D, right? This is high-low A, high-low C, high-low D. And again, we're going to mod it with 2 because it's a 2 high-low. So let's look and see what happens. So like this first one, for example. All right, so it's what? It's ABD, and then mod 2, and they're all low in treatment 1, right? Treatment bracket 1, everybody's low, 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 low. The second contrast is a big 0, mod 2. There's my function for the second one. Okay, so you'll see 1 or 2, we'll see what happens. So that's 0. So I'm mapping 0, 0 into block 1. Oh, okay. And I'm going to map 0, 1 into block 2. I'm going to map 1, 0 into block 3, and 2 1s into block 4. All right, well, let's try it again. So let's go on down here. Let's see. So ABD is a 1. Mod that with 2, I get a 1. The second contrast, ACD is a 1. Mod that with 2, I get a 1. 1, 1 maps into block 4. All right, let's look at B. B is high, everybody's low. So that gets a 1 here, and Everybody else is low. Okay, that maps into block 3. And here's one that's going to map into block 2. Nicely, yeah, okay. So you can see we go down to apply 2 contrast this time. So we've got a primary block, and then the 2 contrasts have four different things, right? They're going to have either 0, 0, 0, 1, 1, 0, or 1, 1. So that's going to map into 4 blocks. Primary block, yeah. Why primary block? Because we said that was the one that had 1 in it. And then second block, third block, and fourth block. So you see the little math here. Let's see, guess how did I do that? I forgot. I think I added them together. Oh, 2 times. Okay, yeah. 2 times that one. Yeah, bless you, plus that plus 1. Yeah, that's a clever way to do that. I forgot how I did it. Yeah. Because you don't have to do this. I'm making this map just to show you. You can go down here and say, oh, that goes to 1, that goes to 4, that goes to 3, that goes to 2, that's a 2. I can come up with an equation. Oh, that was fun. Yeah, I looked at that. So don't think that's some magic equation, right? That's just my way of mapping those 2 digits to 1, 2, 3, 4. You could have done an if statement. I was too lazy. That's pretty funny. So you go down to all the different treatments. Look, all of them ranked, right? 1, AB, then C, then AC. This is every possible combination down here. I've mapped them into blocks. So there you go. Now you've got your assignment. That's how you would have. Now we've done 4 blocks. We've gotten our treatments assigned to 4 blocks, and by assigning them to those 4 blocks, we've compounded this, and automatically compounded that. We haven't confounded something we wanted to. In fact, we've actually done nicely. We've only compounded 1 of the first order interactions. The rest of them we've preserved, and we've compounded these 2 goofy third order interactions, and not this. Not that one. That would have been okay, but who cares about these third order interactions? They're weird anyway and hard to explain. Don't make much sense anyhow. So it's a very interesting way. So now we've assigned our experiments to blocks, 4 different blocks, and made ourselves not compounding something that we wanted to. So let's see. So what's left? So now, so we spent this whole chapter talking about 2Fs, right? 2Fs, 2 levels. Well, we might want 3 levels. Remember that discussion last week? Maybe we've got the money to spend on a low, medium, and high. Can we do this same sort of stuff for 3F? And the answer is yeah, absolutely. With very little differences. So when we do 3F, we got 3 levels, low, medium, and high for F factors. So therefore, we're going to arrange things into multiples of 3 blocks, right? Because if we got 3F, everything's got to be multiple of 3, right? If we have 2 factors, we're going to have 9 experiments. If we have 3 factors, we're going to have 27. So we'd like our blocks arranged to where we got an equal number of things in each block. So we're going to have 3 blocks. If we had 3 squared, we'd have 3 blocks with 3 in each. If we have a 3 cubed, we'd have 6 blocks perhaps, or 3. You can do either one, but you obviously can't have 6 blocks if you only have 9 experiments. So like a 3 squared with 3 blocks. 3 blocks gives you 2 degrees of freedom. So that means we're going to have a 2 degree of freedom factor that's compounded. Let's see. Well, factor A has a 2 degree of freedom, so it could be compounded. It has 2 degrees of freedom, remember, because it has low, medium, and high levels. B has 2 degree of freedom. AB has 4. So one of the things they do is they'll split AB into 2 degree of freedom components and compound those. That way you're still, because you don't, if we're going to compound a 2 degree of freedom thing, we don't want to compound A, we don't want to compound B, but we can't compound AB because it's not 2 degrees of freedom, but if we split it up, it could be. So let's see, so what did they do? Let's see, so one of their examples, let's see, they would like to compound AB and AB squared. So its contrast for AB squared would look like that with a mod 3, because it's 3 levels. So let's try a few examples. Let's see. So let's see. Both A and B were low. 0, 0. On the contrast is a 0. Both A and B high. 2, 6. Mod that with 3. That becomes 0. See, I think I did etc. Yeah, but I didn't leave it at that.
Dr. Press.
Yeah.
Did they choose to mod AB and AB squared because they thought those were two significant relationships, or was that like a formula that?
I think they chose those two because they were just wanting to, you know,
See the interaction between whatever A was and whatever B
I
was.
think they were wanting to primarily see A and B, and it's only a two block. So they're gonna have to compound something. You know, remember our other two block, we had to compound either A, B, or AB. So they didn't want to compound A or B, so they said, okay, well, let's compound AB. You know, I think that's why they chose it. If we're gonna compound something, let's do the least objectionable one to compound. That's what I think they were doing. So let's see. So here's what happened when you apply this contrast to each one of those, each of our three treatments. So, you know, A could be low, B could be low, medium, high. A could be medium, B could be low, medium, high. A could be high, high, medium, could be low, medium, high. So there's our 9 tests, right? Two factors, 3 levels, 3 squared is 9 tests. So here's the contrast on each one of them, A, B, and 2 times B, because in this case, we're compounding A, B squared, A, B, B. So let's see. Each one, A, B squared, so we've got, we're modding it with 3. There's one, mod with 3 there, mod with 3 here, mod with 1. Here. So now, yeah, and just add 1 to it to get the block. 1, 3, 2. So we got 1, 2, 3 treatments of block 1, 3 treatments of block 2, 3 treatments of block 3. Yeah, so it's pretty darn esoteric, isn't it? Yeah. So how did you lay it out? Yeah. So that gives you the layout, right? So the primary one's in block 1. That one's in block 1 where they're A and B are both high. A and B are both medium. A and B are both high in block 1. Yeah. So it's an interesting layout. In fact, I think. I got that. Yeah, example 8, 6. Yeah, example 8, 6. I did this for you. I did the math again on this. So 8, 6. So let's see. So this is the assignment. Well, I can go back to this. So this is your contrast. I did it the other way around here, didn't I? I did A being low, medium, high, low, medium, high, low, medium, high. B, low, low, B, medium, high, high. Got your contrast. Got your block here. Yeah. And so your assignments look like that, right? Let's see. Yeah, 0, 0, and 1, 1, 1, 2, 2. Went to block 1. So it's kind of an odd assignment, isn't it? Look at you got both low, both medium, both high, and then you kind of mix them up over here. You know, you don't keep going like, let's see, A went to high, B went to medium, then A is low and high. It's odd, sort of an odd mix. You know, again, I can't give you an intuitive feel for why it laid out like that for compounding A, B squared. It's interesting. And then, so then I did the ANOVA like they did in the book. Now I'll give you a caveat on this. I did the ANOVA by hand like I did for the others. And I come up with the same conclusion they do, that nobody mattered. But I got some vastly different numbers. And I decided to add this example last night. I had this part last night, just the contrast before, and I said, I'll just do the ANOVA real fast. And so I did it, and it didn't work. And then we had a minor medical emergency in my house, and I didn't get back to revisit it. And so I was like, well, I could not post this and just act like it didn't even exist. And then I said, no, I'll put it in there. Maybe either between next time, you know, we'll figure this out, or maybe somebody else will figure it out. Why? Like I said, I came with the same conclusion they did, and this and this and this are all the same, but my two interactions here are vastly different. And I tried to work it a couple of different ways, and I'm not sure either what I did wrong or what they did wrong. You know, there's not enough details in their guts in this little section for me to see who wins. so if you guys can figure it out, that'd help me too. Right? So anyway, but the conclusion was in this case that nobody had an effect, which in looking at the data they made up, well, it's kind of hard to look at the data because of the way it's mixed and arranged, but you look at that data, it looks kind of random, regardless of what's up and down. You know, it looked like here, hey, A keeps going up, let's see, or if you looked at like, it was probably easier, like look across this line, you're cranking A up. Well, you cranked A up and it went down and then up. It's pretty weird. And then let's see, we're making B go up if we look at that one, that one, and that one, that one, that one, and that one. Yeah, see, B, it went up and then went down. I'm like, yeah, you know, I can see why I got things didn't matter. It sort of looks like everybody's going up and down through their levels. So I'm not surprised. I'm just not understanding why I got really different numbers than they did. So let's see. So again, so how do we end up this? I think the notes are done, right? Let's see, there was no more summary. Yeah, so again, you know, your takeaways are, well what's confounding? It means you goofed up things in how you partitioned stuff, and you've not been able to see an effect. Well, I shouldn't say goof up, just because by the way you've partitioned experiments into blocks, you've hidden an effect, and you can't separate it from the effect of the blocks. So if you do that, that's fine, because you had to do it because you've got a limited number of experiments. The point is make sure you don't do it on something you're looking for, like the main effects. And the question is, well, how do you know that? Well, one, you can look at these contrasts and see what was confounded. And then if you want to confound something not main, like AB interaction or ABC, we can use these contrasts to arrange your experiments in these blocks in a way such that you choose what you confound and not just let it randomly happen. So again, I guess it's a far out topic, but at least you understand what people are talking about when they said they confounded. And this arises again because we stuck ourselves in an odd situation where we're trying to screen. We've got a limited number of experiments because it's long and expensive, and so we were forced to put things in blocks, and we're forced to not do replications. And again, the big way out of this is to, you know, do lots of experiments under the same conditions, but you may not be able to do that. So you understand why this kind of arises and what people are having to do when they're dealing with things like this. And there are ways to handle it, and interesting mathematics associated with it to be able to identify what you hid. So again, it's like trying to relate it back to the vector world, because it's hard to see a space in A, B, and C, D, E mathematics world. But you know, you've moved when you've aligned these blocks with your one of your directions you wanted to see. And so what we're trying to do is, you know, don't move along one of our unit vectors, because we can't see that unit vector. If we are, you know, we can't see its effect. So let's try to move in a direction where we can see what's going on, and see, by see I mean mathematically see. So that's what we're doing. We're trying to be able to look and do some mathematics to understand what these directions are and how they confuse us. So that's it. Again, I think it's an entertaining, interesting topic. I hope you feel that way too. And I wouldn't feel like you're going to be held to your feet to the fire on how to do this kind of stuff. But again, it's getting into the weeds, like we said, design experiments. The takeaway is, don't do this if you can. And boy, if you're going to do screening, do a 2F instead of 3F. It's quicker. And yeah, and if you can somehow maybe, what I do a lot of times when I see things like this, it makes me think, okay, I see that if I am going to do a 2F and I'm going to get this confounding problem, this is going to be a mess. Is there a way I can do my experiments such I can make my experiments quicker, so that I can get them all in the same block and not have to deal with this junk? Maybe that's a good takeaway. Yeah, how can I redesign my physical experiment so it's faster? Or can I do it in simulation? Maybe that's a good thought. Could I do some simulations or calculations to do these 2F experiments, some Monte Carlo things, do them in a computer? Then of course I can replicate them. And of course I don't have background variables in a computer. It's a computer simulation. Do my screening that way, then go do my real tests on the 3 things I got left that I screened out the others with the computer. Maybe I can do that if I got a good model. I don't know, So sometimes I guess it's a backwards conclusion from a lecture, right? Gee, this is a real pain. I don't want to do it. Let me see how I can avoid this. But that's good. rather than just haul off and do experiments over a period of time and make that mistake too. So maybe that's a good thing to learn. So next week we'll put in aliasing with this stuff, which is even more esoteric, but you know, again, it maps into other areas, and the vocabulary and the things you learn will map you into to a particular area. Like I said, the aliasing maps into signal processing, which I heard all the time. I remember as a very young engineer, the first time somebody mentioned aliasing and talking about how important it was, I was like, I have no clue what this is. I don't even know what this guy's saying. And so, you know, at least if you have a clue, you can participate in the discussion without, you know, being over here sweating and worrying, what do they mean, and I can't even follow the discussion. So that'll help. Again, it'll be a similar topic where, wow, this is weird, but you know, it's got some value from that perspective too. So I'm making excuses for the next week's lecture being esoteric too, right? Now, you know, this is the end. This is the end. We've taken away a lot from design experiments, from the beginning stuff. So a few people were asking, maybe try to get everything done by the 8th of December. I think our last class is the first or second. First. So, you know, try to get things wound up, and you know, if a few of the assignments are pushing you, you know, interact with me or whatever. Don't sweat too much. This is the last class, and I want you to end on a sour note. Right? We're all kind of done. So, but you know, try to get most of it all done by the 8th. And if you need a little extra time, let me know, because I think exams don't be until the 14th. And so my grades, I don't know when they're due, but they're not going to be due for a while after that, a day or two at least. So we've got some time. Thanksgiving's coming up. Yeah, so anyway, I hope you thought that was fun and entertaining. Odd, but entertaining, interesting topic. It's weird, doesn't it? It's deep. Yeah. No, I like the mathematics, and I like the way it works. It's kind of funny when things like that work. Do these calculations and it splits it up.